The International Math Olympiad, often called the IMO, is a prestigious math contest that gathers high school students from around the globe to test their problem-solving skills. The competition spans 2 days, with each day featuring an exam lasting 4.5 hours. There are just 3 problems to solve per day, with the problems going from hard to harder to hardest. Today I'll share with you the last problem on the 1970 IMO. Here's the problem. In a plane, there are 100 points. Okay, here are 100 points. Now, no 3 of which are collinear. That means we don't have 3 points on the same line like this. Next, consider all possible triangles having these points as vertices. Okay, from these 100 points, we examine every triple of points. Now we see why the problem specified no 3 collinear points. That way, every triple forms a legitimate triangle, not a degenerate triangle. Finally, what's the problem asking? Prove that no more than 70% of these triangles are acute angled. In this video, we'll solve the problem. We'll actually do better, improving the bound of 70%. We'll end with an open problem. First, just a quick reminder on terminology. An acute angle has less than 90 degrees, a right angle has exactly 90 degrees, and an obtuse angle has more than 90 degrees. We'll apply these same names to triangles. A triangle is acute or acute angled if all 3 of its angles are acute. A right triangle has a right angle, and an obtuse triangle has an obtuse angle. In other words, the type of a triangle is the same type as its biggest angle. Next, let's revisit the original problem. Here it is again. We have 100 points. We have to consider all triangles on these points. That's a lot of triangles. How does one even begin to tackle such a problem? Where's the starting point? As with many complex problems, it helps to start with a simpler case. What's the simplest non-trivial case of this problem? I would say 4 points instead of 100. Okay, let's examine the case with just 4 points. Here are 4 points. We're supposed to consider all the triangles on these 4 points. How many triangles are there? Well, here's one triangle, here's a second, and a third, and finally a 4th triangle. There are 4 triangles on 4 points. Of these 4 triangles, how many are acute? The answer depends on our starting 4 points. What can our 4 points look like? There are 2 cases. One case is when all 4 points are on the outside like this. The 4 points are the vertices of a convex quadrilateral. And here's the second case. The convex hull is a triangle with 1 point inside the triangle. Let's analyze each case separately. Here's the outside case. Of the 4 triangles on these 4 points, how many can be acute? To start, let's draw the 4 angles of the quadrilateral. Okay, here are the 4 angles in red. What can we say about the 4 angles of this quadrilateral? Yes, the 4 angles add up to 360 degrees. That means the average of the angles is 90 degrees. What does that imply about the biggest of the 4 angles? It has to be at least 90 degrees. In other words, the biggest angle is not acute. For example, in the picture, the bottom angle is not acute. What does that mean about the triangles? It means at least one of the triangles is not acute. In the picture, the bottom triangle is not acute. Okay, we made progress on the outside case. Let's switch to the second case. Here's the inside case. Let's draw segments from the inner point to the outer points. Now let's look at the angles around the inner point. What do those 3 angles add up to? Yes, 360 degrees. We're going around a circle. So the average of the 3 angles is 120 degrees. What does that say about the biggest angle? It has to be at least 120 degrees, meaning it's obtuse. In the picture, the bottom angle looks to be the biggest, and it is obtuse. And what does that say about the triangles? At least one of the triangles is obtuse. In the example, the bottom triangle is obtuse. So again, we found at least one triangle that is not acute. Okay, we've looked at both cases. Let's summarize. Here are the 2 cases again. There are 4 triangles. In each case, we showed that at least one of the triangles is not acute. So that means at most 3 of the triangles are acute. That's nice. We're going to find it helpful to restate that result in multiple ways. Here are 4 points, forming 4 triangles. From the counting view, We showed that at most 3 of the triangles are acute. So what fraction of triangles are acute? We know that at most 3/4 of the triangles are acute. What does that mean as a percent? At most 75% of the triangles are acute. In the original problem, we wanted to show at most 70%, but remember the original problem had 100 points, not 4 points. These are 3 ways of saying the same thing. We'll find it helpful to say it in one more way. Here we'll look at the problem from a random view. We'll start with 4 points that are fixed. Suppose we choose 3 of the 4 points randomly, all triples being equally likely. Here I've chosen 3 points in red. We're interested in triangles, so let's draw a triangle on them. What can we say about the probability that the resulting triangle is acute? It's at most 3/4. That's just another way to restate our result. It might seem weird to restate the same result in many ways, but later it will turn out to be quite useful to have this random view. Okay, we've analyzed 4 points as much as we can. What's next? Let's go to 5 points. Okay, here are 5 points. First, we need to know how many triangles can be made out of them. The number of triangles is the binomial coefficient 5 choose 3. That's 5 times 4 times 3 over 3 factorial. That makes sense because there are 5 choices for the first vertex, 4 choices for the second, and 3 choices for the third. We divide by 3 factorial because, for example, we don't want to count ABC and ACB as different triangles. We get 60 over 6, so there are 10 triangles on 5 points. Next, we need to count how many triangles are acute. The count depends on the exact configuration of the 5 points. We may have to split into cases. One case is when the 5 points form a convex pentagon, with all 5 points on the outside. A second case is when the convex hull is a quadrilateral, with 1 point inside. Are there any other cases? Yes, the convex hull could be a triangle, with 2 points inside, and we don't know where those 2 points are located. The cases are getting messy. We may have to divide some of these cases into subcases. We could make this approach work, but it doesn't look pleasant. Let's try another approach. We'll try to use our previous work on 4 points. To do so, let's look at the random view again. Okay, we start with 5 points that are fixed. In the random view, we'll choose 3 of the points at random. I've chosen the 3 red points. Let's draw a triangle. We'd like to know the probability that the resulting triangle is acute. And that probability is, I don't know. We have nothing to work with. We haven't used our previous work yet. How can we use 4 points? Here's an idea. We won't choose 3 points directly. Instead, we'll choose 4 points. 4 points at random. I've colored them yellow. Then we'll choose 3 points. 3 of the 4 points at random. I've colored those 3 red. This 2-step process is equivalent to choosing 3 of the 5 points at random. We just did it with an intermediate step. What's the advantage of this 2-step procedure? Now we can exploit our previous result on 4 points. For example, what's the probability that the resulting triangle is acute? No matter which 4 points we chose on the first step, the probability of the triangle being acute is at most 3/4. That's what we showed in the 4-point case, so it automatically carries over to the 5-point case. This is a crucial step, so let me say it again. Each 4-point probability is at most 3/4, and the 5-point probability is the average of the 4-point probability. So the 5-point probability is at most 3/4 as well. Okay, we made progress on the 5-point case by thinking randomly. Let's look at the 5-point case in other ways. For example, we can look at the fractional view. With 5 points, what fraction of the triangles will be acute? It's at most 3/4. That follows from the random view. Next, let's turn to the counting view. What can we say about the number of acute triangles? It's at most 3/4 of 10. That's because at most 3/4 of the triangles are acute, and there are 10 triangles. 3/4 of 10 is 7.5, so the number of acute triangles is at most 7.5. But we can't have half a triangle, so what's a better bound on the number of acute triangles? It's at most 7. The counting view has given us a free improvement from 7.5 to 7. Next, let's translate that bound back to the other views. We know that at most 7 of the 10 triangles are acute. So what does that say about the fraction of acute triangles? It's at most 7/10. And what does that say about the percent of acute triangles? It's at most 70%. So what can we say about the probability of a random triangle being acute? It's at most 7/10. By switching between the multiple views, we get a free improvement of the bound from 75% to 70%. Remember that 70% was the bound in the original problem. So we're on the right track. We've analyzed the problem for 5 points and for 4 points and for 5 points. What's next? We could go on to 6 points, but now that we've reached the 70% mark, let's go straight to 100 points. Okay, here are 100 points. That may seem intimidating, but we can rely on our previous work. We'll use the random view again. We'll start with 100 points that are fixed. Our problem is about triangles, so the most natural idea is to choose 3 of the points at random. But we've seen that making that choice directly is not the best. We want to rely on our previous work. We've reached the 70% mark with 5 points, so let's choose 5 points. We've chosen 5 points at random, colored yellow. Now what? We'll choose 3 of those 5 points. I've colored them red. That 2-step process is equivalent to choosing 3 out of 100 points in 1 step, but it will be easier to analyze this way. What's the probability that the resulting triangle is acute? No matter which 5 points we choose, we know that the probability of a triangle being acute is at most 70%, which is 7/10. So the overall probability is at most 7/10. Great! That was the random view. Let's look at this result from other views. From a fractional view, the fraction of triangles that are acute is at most 7/10. What about this percentage view? At most 70% of the triangles are acute. That's what we wanted to show. Yay! Let's look back at the original problem to be sure. Yes, we have 100 points. We look at all triangles among those 100 points. We showed that at most 70% of those triangles are acute. Mission accomplished. When mathematicians solve a problem, we celebrate for 1 minute, but then we think about whether we can improve or generalize the solution. How can we improve the solution? One way is to wonder whether 70% is the best bound. Can we reduce that percentage? Let's try. First, let's quickly summarize our original solution. We originally showed that for 4 points, at most 75% of the triangles are acute. Then we went to 5 points, getting a bound of 70%. Finally, we jumped straight to 100 points, again getting a bound of 70%. But instead, we could have kept going to 6 points, 7 points, and so on. Doing so could have led to better bounds. For 6 points, we get the same 70% bound, but for 7 points, we can get a bound lower than 69%. We'll see why later, but we'll just use the same approach as before, switching between the random view and the counting view. And for 8 points, we'll get a bound lower than 68%, and so on. I'll say more in a bit about where these bounds are coming from, but before that, we'll need to count the total number of triangles. Suppose we have n points. How many triangles can we form on them? It's the binomial coefficient, n choose 3. That's n times n minus 1 times n minus 2 over 3 factorial, which is 6. As an example, suppose we have 7 points. How many triangles are there? There are 7 times 6 times 5 over 6. That simplifies to 35. Okay, next we need a good bound on the number of acute triangles. We'll express our bound using an interesting sequence of numbers. A of 4 is 3 because on 4 points there are at most 3 acute triangles. And A of 5 is 7 because on 5 points there are at most 7 acute triangles. Where did I get the other numbers? I set up a recurrence equation. Here it is. The base case sets A of 4 to 3. The general case defines A of n in terms of A of n minus 1, as you see here. Where did this equation come from? is the same as our previous work on the random view versus the counting view. Note that a of n-1 over n-1 choose 3 is just a bound on the fraction of acute triangles on n-1 points. Multiplying that fraction by n choose 3 gives a bound on the number of acute triangles on n points. That product might not be an integer, so the half brackets here mean take the floor of that expression. Floor means lower the expression until we hit an integer. That recurrence will define an infinite sequence of numbers. Let's see an example. We'll calculate a of 5. Here's the expression. We can plug in. We get the floor of 3/4 of 10. That's the floor of 7.5, which is 7. That's the same calculation we saw before when we handled 5 points. That's why our recurrence gives a bound on the number of acute triangles. Indeed, that's what our next result states. For n points, the number of acute triangles on them is at most a of n. The proof of this claim is to mimic exactly what we did before to go from 4 points to 5 points. From the random view, having a bound on the n-1 point case gives a bound on the n point case. So now we know that the A sequence is useful to the acute problem. Let's calculate some terms of the A sequence. Here I've started a table. The first column is n, the number of points. The second column is a of n, an upper bound on the number of acute triangles. The third column is n choose 3, the total number of triangles on n points. The final column is the second column divided by the third column, expressed as a percent. It's an upper bound on the percent of acute triangles. I started with 4 points and 5 points, which we already know about. Let's go to 6 points. The percent bound remains at 70%. Next, 7 points. Already, we get an improvement. We get 24 acute triangles at most out of 35. The bound has gone below 69%. Next, 8 points. Now the bound is less than 68%. We can keep going like this 1 point at a time. By the time we reach 16 points, the bound is less than 67%. So far, I did these calculations by hand. For the rest, I used a computer. I wrote a little 5-line program. When I got to 100 points, here's what the computer told me. There are at most 107,811 acute triangles out of a total of 161,700 triangles. As a percent, that's about 66.673%. So we've improved the IMO problem, reducing the bound from 70% to under 67%. The bound for 100 points is 66.6 something percent. Does that ring a bell? It seems suspiciously close to 2/3, and indeed, that's what our bounds are converging to. By staring at our data, and in particular by calculating how far the bounds were from 2/3, I was able to guess a formula for a of n. Here's the formula. The main term is 2/3 of n choose 3, but there's also a secondary term. Once we guessed the formula, it's straightforward to prove it. We can use induction on n. Our recurrence for a goes from n-1 to n. That's tailor-made for an induction proof, also going from n-1 to n. The main term of the formula is cubic in n, whereas the secondary term is only linear in n. So in the limit, we can just focus on the main term. As n approaches infinity, our fractional bound approaches 2/3. Okay, so far our bounds have all been upper bounds. Namely, we've shown that the number, or fraction, or percent of acute triangles is at most such and such. What about lower bounds? By that I mean, can we find an example, a construction of, say, 100 points with a large fraction of acute triangles? Let's find out. Here are 100 points. I've placed them on a circle. They're spaced evenly around the circle. Our question for now is, about what fraction of the triangles formed by these points are acute? As the number of points gets larger, it feels like the points will sort of cover the entire circle, and so we can pose a continuous version of our question. We have a circle. We choose 3 points on the circle at random. The 3 points form a triangle. Our new question is, what's the probability that the triangle will be acute? This is a classic question, going back decades at least. If you haven't seen this question before, feel free to pause the video and think about it. It's a fun question. Okay, I'll go over one solution now. Instead of choosing the 3 points right away, we'll take our time. First, we'll choose point A at random. Then we'll choose a random diameter of the circle. In the picture, the white chord is a diameter going through the center of the circle. We'll choose the diameter at random. Imagine spinning the diameter around the circle until it stops in a random direction. Then we'll choose B to be one of the 2 endpoints of the diameter. We make that choice by flipping a coin. Note that B is a random point on the circle. We just chose it in a 2-step process. We'll see later why we did such a 2-step procedure. Next, we'll do the same for point C. We'll choose a random diameter. Then we'll choose C to be a random endpoint of that diameter. Point C is also a random point on the circle. Now our question, what's the probability that triangle ABC is acute? To solve this random question, we'll first solve a non-random question. In the non-random question, we have the diagram you see here. We have a point A on a circle. We have 2 diameters of the circle. One diameter has endpoints B1 and B2. The other diameter has endpoints C1 and C2. The only assumption we'll make is that the 5 points are different. Now here's what we'll do. We'll consider 4 triangles in this picture. We'll choose as one vertex point A. The second vertex will be either B1 or B2. The third vertex of the triangle will be either C1 or C2. That will create 4 different possible triangles. So here's our question. Of those 4 triangles, how many are acute? You might think the answer depends on the points, but it doesn't. One and only one of those triangles is acute. Namely, start at A and imagine walking around the circle in both directions. Look for the 2 points that are not adjacent to A. In this picture, it's B1 and C2. Then the triangle AB1, C2 will be the only acute triangle. Notice that this question was entirely deterministic, not random at all. It's a common tactic in probability to solve a random question by first solving a non-random question. Okay, let's go back to our random question. We have 3 random points A, B, and C on a circle. What's the probability that the triangle ABC is acute? Imagine we fixed the point A and the 2 diameters. Our previous work showed that of the 4 choices for B and C, only one leads to an acute triangle. So what's the probability of being acute? It's 1/4. Wasn't that a slick solution? There are other solutions too, but I like this one. Once we started this whole discussion by looking at a finite number of points on the circle, spaced evenly. Our work on the continuous problem will help us solve this question. Namely, as the number of points heads to infinity, the fraction of acute triangles heads to 1/4, or 25%. It's particularly clear when the number of points is even, because then the notion of diameter carries over. But either way, the percent of acute triangles will head to 25%. I won't say more here, because we'll soon find an approved example that beats the 25%. 25% was good for a first attempt, but we can do better. I'll start with this triangle. The angle at point B is nearly a right angle. It's just a little smaller. Think of 89 degrees. We'll make the angles at A and C equal to each other, so those 2 angles will be a little more than 45 degrees. We'll now sprinkle in lots of points. The new points are in green. We'll put 1/3 of them near A, 1/3 near B, and 1/3 near C. The new points are in little circular arcs around A, B, and C. What fraction of the triangles on the green points will be acute? It turns out that if we place the green points carefully, we can get about 5/9 of the triangles on the green points to be acute. For example, if the triangle has 1 green point near A, 1 near B, and 1 near C, then the triangle will be acute, assuming we place the green points carefully. In the video description, I'll include a link with more details. So let's summarize our bounds. Suppose we have n points where n is large. Think of n as beyond 1,000,000, heading to infinity. What's the largest fraction of acute triangles we can have? Here are the bounds we've shown. As an upper bound, we've shown that at most 2/3 or so of the triangles are acute. On the other hand, as a lower bound, we've sketched a construction where more than 5/9 of the triangles are acute. The largest fraction of acute triangles, therefore, is between 5/9 and 2/3. That leaves an open problem. Is the largest fraction of acute triangles near 5/9, near 2/3, or somewhere in between, like 60%? I don't know. Maybe you, dear viewer, can make progress on this question. Well, that was a fun and challenging problem from the IMO. After we've conquered a challenging problem like it's worth spending a little time to reflect on the solution. Let's extract some strategies we can take away from our journey. First, keep asking simpler versions of the question until you can solve one of those iterations. In this instance, we began with the 4-point case. Second, leverage work on a simple case to tackle a harder case. Here we use the 4-point case to solve a 5-point case, and then we use the 5-point case to solve higher cases. Lastly, look at the problem from multiple perspectives. For example, here we made progress by alternating between the random view and the counting view. At first sight, the problem looked like pure geometry, but our solution was more about methods from probability and combinatorics. In the video description, you'll find several links and references for further exploration. Thanks for watching!